Okay guys, math6610, this video is on categorical data analysis, and we're going to look at chi-square, goodness of fit, and the test of independence. The goodness of fit, I don't consider it to be as important, but I want to run through a quick example just so you have it on your radar in case you ever on a deserted island. They tell you if you can work a goodness of fit test, they'll let you off. Well, you'll be prepared. All right, so we'll get through this quickly, and then we'll get to the test of independence, which I think is the most important one. Guys, this test, the chi-square test of independence and goodness of fit test, has as its underlying sampling distribution the chi-square distribution, and the chi-square distribution has one number that's the degrees of freedom. Now, the degrees of freedom is not one. The degrees of freedom could be 2, 3, 4, but there's only one number. And I mention that because the chi-square distribution kind of reminds you of the F distribution. And the F distribution has 2 degrees of freedom. If we're in the ANOVA case, it's the the degrees of freedom for the numerator and the denominator. Nevertheless, what happens is very similar to the F distribution. If we're calculating the p-value, we take our test statistic, and the area to the right of the test statistic is the p-value. We don't get into a two-tailed test in this situation. It's all area in the right of the distribution. All right, gang, just a little bit of review. After just teaching this class within the last month, what gave students the most difficulty was knowing what test went with what scenario. So in an attempt to make things clearer throughout the term, I'm going to review this little by little. So if we think about what we've done so far, we've looked at a t-test, and that's really just a claim about a quantitative measurement. So if we're working in a school district and someone makes the claim that the average ACT for students in our district is 21, well, we could test that claim with a t-test. A two-sample t-test looks at a quantitative variable across a categorical variable with 2 groups. So if someone wanted to test, like we did in the previous video with SATs, the equality of ACTs across gender, we would have a quantitative variable with ACT, and we would have gender with 2 groups, which is appropriate for a two-sample independent t-test. The two-sample matched pairs t-test reminds you a lot of the independent samples t-test. In fact, they're confused sometimes. I've never seen anyone in a situation where they needed to use an independent samples t-test use a dependent, but I've seen the reverse happen quite a bit when someone has a matched pairs design and they inappropriately use an independent samples t-test. But anyway, guys, at the end of the day, a matched pairs, you're going to have measurements on the same subjects at different time intervals. Now, if we have 2 measurements, and think pre-test, post-test, on the same people, excuse me. Get some coffee here. Then we have matched pairs. But if we would have multiple measures, let's say we take measurements throughout a term, maybe 5 or 6 places on a student, then we get into what's called a repeated measures design, which we'll study here in about, 10 weeks, something like that. All right, gang, goodness of fit test. Let's look at the just a very simple example. First of all, think categorical data. When you see categorical data only with no quantitative variable included, think chi-square. So I'm going to set up a very, very simple situation. So let's say a newspaper, media, whatever it may be, makes the claim that 40% of people in a state intend to vote for candidate A, 32% candidate B, and 28% for candidate C. You suspect the claim, you'd like to test it. First thing you do is set up an appropriate null and alternative hypothesis. It's kind of just the foundation of scientific inquiry. And I would set up the null and alternative exactly like this. I see no reason not to test at the 0.05 threshold, so we'll go for it. Guys, the next thing we need to do, and this should be very clear to you by now, as we calculate the test statistic and the p-value. But the first thing we would need to do is go out and collect a sample, hopefully a random sample from our population. So let's just assume for this illustration that we got 1,000 people, and we ask them, who are you going to vote for? Hence making it categorical, because they're either going to vote for candidate A, B, or C. And let's say we get the following counts. I hope that adds up to 1,000. It does. Okay. The next thing we would need to do is we'd need to create what's called the observed and expected matrix. Now, the observed matrix, the one I've just put the check beside, is very simple. It's just the observed counts from our sample. The expected matrix is a little more difficult. The expected matrix is created under the belief, under the assumption that the null hypothesis is true. Well, if we go back to the null hypothesis, the claim in the media organization was that 40% of people in this state would intended to vote for candidate A. Well, if we have 1,000 people in our sample, then we would expect under the null hypothesis to get a count of 400 for candidate A, 320 for candidate B, and 280 for candidate C. Guys, the next thing we do is we calculate the chi-square statistic. We're going to run from 1 to 3, obvious reasons, 1, 2, 3 groups. And the test statistic is we take the observed minus the expected squared divided by the expected. So guys, our chi-square statistic, I've written out each term for you, and I've provided the summary at the bottom. What I want you to notice is that these two observations right here for candidate A and candidate C provide the most influence in our final test statistic. So we would say under the null hypothesis, our sample data is 7.53 standard errors above the mean. Okay? Pretty simple stuff. Now the next thing we need to do is we need to calculate our degrees of freedom. And the degrees of freedom for this situation is very simple. It's just k minus 1, where k is the number of groups. So we have 3 candidates. So guys, we are dealing with the chi-square distribution, degrees of freedom equal to 2. So guys, whatever that looks like, and I happen to know it's going to look something like that. Let's get the 2 up there. We can shoot. All right. So what we need to do is we need to find the area. What was it? 7.53. We need to find the area to the right of the curve. Well, guys, what I'm going to do is I'm going to use R. It works. So I need the p-value, so I'm going to have p, chi-square. And I remember I need the area below, so I'm going to have to do 1 minus. And I went 7.53, comma, degrees of freedom 2. Alright gang, so my p-value is going to be 0.0232. I'm going to write this down while I'm at it because I'll forget it. So 0.0232. Because because we're going to need that. All right, gang, let's go back to the blackboard. So 0.032. Guys, that's pretty significant evidence against the null. So not to get too crazy here, but I'm going to draw a line through that because, again, there's more support in this case. There we go. There's more support for the alternative hypothesis than the null hypothesis. Now, what that tells us is there appears to be one of the percentages that's different. So, what I would want you to do next, again, at this stage of the game, let's step back a little bit. At this stage of the game, we know that at least one percentage appears to be different. There's no really high confidence interval that we can construct for this. What we'd want to do is we'd want to get into looking at a standardized residual, and I'm going to wait and illustrate that in the test of independence. All right, because I don't want to spend a lot of time on the chi-square goodness of fit when most of our attention is going to be on the chi-square test of independence. Now, let me just show you briefly how you would, very quickly, how you would set this up in R. So I would call this the probabilities, and this is under the null hypothesis. And the next thing I would call would be my count, and this is what I get from my sample data. And then I would run just a chi-square test of my count over my probability. Well, actually I have to do this. I have to do P equal probability. All right, gang, what happened? Well, let's see what happened. Count should be 360. You're probably thinking, where in the heck did that come from? All right, let's try this again. So we want counts, P equal probability, and then we get a situation where the answer matches up. Guys, what I did a typo here. Looking at my notes there, and I typed 380 there instead of 330. So guys, under the null hypothesis, we would reject and assume that percentages are different. Now, what we could do is we could go into each one and run a one proportion z-test and go from there. All right, gang, let's get into what I think is the most important part of this. Okay, getting everything set up here. All right, gang, what I want to illustrate now is the chi-square of independence. And let's generate this with an example. And let's say we want to take a look at level of smoking. And exercise. And we want to take a look at the relationship between the level that someone smokes and the level at which they exercise. And let's say that we've categorized level of smoking as heavy, never, occasional, and regular. And let's say that we categorize exercise as frequent, never, and some. So let's say we've collected the following data. And our exercise is frequent, never, and some. And let's say we have the following. Now, the first thing I'd want to do is get my row counts and my column counts, and then ultimately I'd want to get a total count. And I'm just going to do a couple of these. So this would clearly be 11, and that would clearly be 17. And I'll let you guys do this, 21, 22, 23. And you guys can fill those in. But first of all, before going any further, I want to get a total sample count. And if my calculator entries are correct, it looks like we got 236. Now, just like before, we need to have an observed and expected matrix. But before we go any further, let's officially state what we're going to test here. So we would say the null is it's smoking, level, and exercise are independent. You guys, independent is just a fancy smancy name for saying not related. Our alternative hypothesis are dependent. Now, if you don't like the whole independent, dependent, sometimes it's easier to think of not related and related. So the level at which someone smokes and their exercise habits have no bearing on one another. They're not related. Our alternative hypothesis is they are related. Guys, the observed matrix is just going to be the counts just as we have from the table before. Now, our expected counts is calculated by taking the row sum times the column sum divided by cap n, which is the grand sample size. And guys, in this situation, our grand sample size, the sum of all the sample elements is 236. So the expected cell count, I'm not going to do all these. For heavy and frequent. So guys, this is the smoking, and this is the exercise. Is going to be what? Well, we go back to the row sum, 11. Now we need the column sum. And I didn't do that. So what do we get there? 94, 106. Let's see. 9 plus 12 plus 87 plus 7. So 115. Does that seem reasonable? Yeah. So under the null hypothesis, the expected cell count for the upper left-hand entry would be 5.36. Now, should you round that? No, absolutely not. Just keep it, even though we're looking at counts, we would leave it at 5.36. So guys, the expected cell count, again, we're going to have 9 entries, 5.36. Just so everyone's on board with me, let's calculate the expected cell count for this, which would be regular smoker and never exercise. So guys, the cell count there, the row count would be 17. The column is 1923. And we're at 236. Yeah. So we're going to have 1.66. Now I'm not going to go through all the calculations, but the chi-square statistic is still the sum of the observed minus expected squared over the expected. And guys, and each in this we would have 9 entries. Okay. And you know, in all your spare time, you can you can run through that. Now, in this situation, for the chi-square test of independence, our degrees of freedom are the number of rows minus 1 times the number of columns minus 1. So in this situation, we have 4 rows. And we have 3 columns. So we would have 6 degrees of freedom in modeling the calculation of our p-value. Okay. Now, what I want to do now is I want to get out of this and go into R, and let's just show how we would set this up using R. So that's the way we would test. We would run a chi-square test of independence if we were going to actually do it in the education setting. So guys, I'm going to call first thing row 1, and I'm just going to type in the entries. Let me go get them. And I'm going to call this row 2 because I'm really not clever enough to call it anything else. You may call it heavy, never, occasional, regular, but I'm not going to do that. Okay, next thing we do is kind of clever. We'll actually bind these. So we do what's called a row bind. And I tell you what, I'm just going to call it data. We'll go R bind, row 1, row 2, row 3, row 4. If we look at data, then we've got the matrix exactly as we need it. Next thing we'll do is we'll run the chi-square. So, and I'm going to call this just chi-square test. So I'm going to call it something because we're going to need this to do some stuff coming up. So guys, just as before, it is chi-square test, and I want to do it of my data. Okay, I get a warning here that the chi-square approximation may be incorrect. Okay, let's just go ahead. I'm pretty sure I know what's going on here. So if we type chi-square test, we get the results of our analysis. And first of all, we can look at the chi-square. This is the test statistic, and just as we expected, we have 6 degrees of freedom, and the p-value is 0.4828. Now, by hand, if we were going to calculate the test statistic, we would do 5.4885. Degrees of freedom 6. You can see we get the same p-value. Now, what we know here is we don't have evidence to reject the null, so we assume, statistically speaking, that there's no relationship between smoking and exercise level. But we've got this this red warning up here. The chi-square approximation may be incorrect. Now, let me come in with a hashtag here. The reason we received the error, most likely, I don't know because I haven't done this, is we've violated an important assumption. And one of the important assumptions for the chi-square test of independence is that each expected cell count must be higher than 5. So what I can do here, and you can see that I have a very, very small cell counts here, 1 and 1. So it kind of makes sense that again, this is the observed matrix, so don't get that confused. But it makes sense that the expected cell count in some cell may be less than 5. So what I can do here is I can go, okay, this is the reason I saved this back here. What I can do is I can take that, which I'm going to call chi-square test, and I can put a $sign there and just type expected. Now what this is going to do, it's going to give me my expected cell count, and we did, let me go back to the expected cell counts that we did before. So we had 5.36, and at the bottom we had 1.66. So yeah, I didn't see any reason to illustrate all 9 for you. You guys are smart folks. I illustrated this one, just to give you those answers. So you can see I've got expected cell counts. I've got 3 expected cell counts less than 5. So that's the reason that I got the red warning back here. Now, another thing I want you to be able to calculate, we need to be able to calculate the standardized residuals. And the way, all right guys, as fate would have it, the computer crashed, and well, actually QuickTime quit on me and crashed. So fun stuff. So this is the reason things look a little bit different. I've about 15 minutes has passed. You're not going to see the 15 minutes. You're going to see hopefully a kind of a smooth transition from where we were into where I am now. So I've restarted R, typed my data in again, and let's just go ahead and run the test as we did before. And you're going to see we get the same warning message, but if we type test, we get the same p-value. What I did before is I created the expected cell counts, and I did test $expected, and so interpretation, for example, of the 5.36. Now, let me show you something. Something just hit me that would probably really help in a situation like this. There's a function that's called dim names for data. That's what we call our data. And what we can do here is we can do what's called list. And in the column, or in the, let's see, we do the rows first, right? Yeah. So I can do smoking equals the list of heavy. Never. Occasional. And regular. And then I can go exercise equal, and I think we had what, frequent, none. So what this is going to do, and you've probably figured it out, sum. Now if we do data, we get the dimension names on the columns, and this is going to help, I think, in where I'm going to be headed here. So what we can say here is if we do now test, I'm not sure whether this will include it in the expected. No, it won't, so we'd have to go in and set that up. But what we get here is we get the expected cell count, and we can see again, as I explained earlier, because these expected cell counts are less than 5, we get into an issue. Now, let's get into the standardized residuals. So if I go test $STD RES, I'll get the standardized residuals. Oh, shoot, just a $. Here we go. So we get the standardized residuals. And the standardized residuals are important, especially if we reject the null. Now the red flags here are standardized residuals that are above 2 or below -2, and those are usually apparent, usually occur when we reject the null hypothesis. So guys, let's think this through. The null hypothesis is smoking and exercise are not related. If we reject that, we conclude that smoking and exercise are related. Not the case here, but if p-value is less than 0.05, that would be the case. What the standardized residual allows us to do is it allows us to go down and break down the level of exercise and the level of smoking that had significant effects or had major impacts, if you will, on the final decision to reject the null. Now I want to interpret one of these for you. So let's just go this one, row 2, column 3. So you can see up here that this is the occasional smoker with some exercise. So the interpretation of that would be the observed cell count for the occasional smoker who exhibits some exercise is 1.82 standard errors above, I'm going to put that in because we have a positive, the expected cell count. So the cell count that provides the most contributing factor would be this one. And actually this is the observed cell count is less than we would have expected it to be. So those who are occasional smokers and exhibit some exercise is 1.89 standard errors lower than we would have expected it to be. Alright gang, so what should we do? About the warning. Really there's two solutions here. One solution, if we were going to try to publish this, is we could just go ahead and publish the results but make a note that the p-value isn't stable because of the violating the assumptions. Now guys, assumptions are going to play a major role from here on out in the statistical analysis that we explore. I'm going to tell you right now, if this is a referee journal, it's not going to happen. We would either need to increase the sample size to where we get our expected cell counts all above 5, or another potential possible solution to this is to combine groups. Now, and that's what I'm going to do here, kind of on the fly. What I would take a look at is I would see that row 1 and row 3 and row 4 exhibit some level of smoking. Row 2 doesn't. So what I would probably do here is I would create a new row, and I would take row 1 plus row 3 plus row 4. So what I'm doing here is I'm combining the rows of some level of smoking, heavy, occasional, and regularly. So I've got a new row. Now I'm going to create a new data. Let's call this data 2. So I would go rbind, and I would have my new row along with row 2. So when I get data 2, I'm going to end up with these values. Now, I would kind of like to come in and do this, these dim names again, because it just really makes it nice to be able to identify the names. So I'm going to copy this and paste it because I think it's going to beat the alternative. So first of all, I don't need data, I need data 2. And smoking, I don't need 4 rows, I just need 2. So the new row was smoker. And this one would be, I'll tell you what, let's keep it simple. Smoke, no, yes. Okay, so 1 is yes, right? New row, yeah. And exercise, we'll keep it as is. All right. So when we do data 2, we get into labels that make sense. Okay, now I still have issues with this with this low expected or this low observed cell count, but you know, let's make it happen. So I'm going to call this test 2. Cos chi² test, and I want data 2. Okay, so again we have a warning. That's no fun. And we still don't reject the null. So guys, if you got any friends out there smokers, it doesn't appear there's any relationship between them smoking and not smoking and their level, or well, exercising or not exercising. So let's go ahead and get the expected cell counts. So I have test 2, $, expected, and I'm expecting something under 5, yeah, barely. So guys, we gave you know, a good effort. I guess what I would probably do here, I'm not going to because this video is going to be like long anyway, but I would probably combine frequent and sum and create a 2x2. Now if you get into a 2x2, you have to do what's called a Yates continuity correction. So just a word of caution, you'd have to explore that. So guys, you know, if I really wanted to publish this, I guess what I would do is probably bump up the sample size and you know, try to get more people in my random sample, or again, seriously consider adding these two. But still, this cell count right here is going to give us issues. So guys, that's all I got. That's an illustration. Well, let me say one thing. How would we write this up? So how what would the write-up look like? I would say something to the effect, there was not a statistically significant association between levels of smoking and levels of exercise, well, and frequency of so I would come in with the chi² symbol. Degrees of freedom were 6. The chi² statistic was 5.49. And our p-value was greater than 0.05. After recoding, okay, the minimum expected cell count assumption was violated, so the data was recoded into smoking and non-smoking with the same levels of frequency of exercise. The test was also not statistically significant. And guys, just go ahead and you know, report the chi² symbol. Degrees of freedom in this case wouldn't have been 6, would have been 2, I think. Yeah, and you know, just to get into the same situation. If we have any expected, or I'm sorry, any standardized residuals higher than 2 or -2, that would be something that you definitely want to point out in your write-up. So guys, this has been a frustrating video. You're only going to see parts of it. So oh well. So guys, have a good one. Take care.